tomography, standard X-ray tomography as well, and this would fit in as well. Then I come to more general convex Tikhonov regularization, and then something very old actually, but something new. There's a new paper just recently appeared by Antonin Jean-Paul and Gabriel Perret on TV regularization. And you see in R2, which is the challenge for us maybe to get more results in this field in higher dimensions, but currently it just works in R2, so this is something pretty new. And finally, if time allows, but I'm not sure if I have time, I will tell you on some generalizations of the theory to some non-convex regularization problems. So, the problem is actually very general, which I'm stating here. So what I would like to do is I would like to solve an pointer actually. I would like to find minimal energy solutions of these equations. So in an abstract setting, I just have an equation, typically a linear equation. It could be a nonlinear one as well later on. But in the beginning, I just concentrate on linear problems, and I want to find a solution which has the minimal energy, meaning that it minimizes this convex function. So I assume that the operator k here is a linear bounded operator, and for the sake of simplicity, I consider, I don't need much more, so it's not just simplicity. But I assume that the operator is defined between Hilbert spaces. It's more fashionable to do it in Banach spaces, but for my purposes it's more or less convenient. I can always embed them into a Banach space. And what I assume is that the operator is compact, so it maps bounded sequences onto, at least in a weak sense, to convergent sequences. And in this sense, the operator then is, the solution of the operator equation is ill-posed, meaning that if I have a perturbation in the data G, it could mean that I have not the solution of this equation anymore, but it also could mean that the solution is relatively far away from the expected solution. And whenever there appears a delta, and I hope I'm consistent, then this should always mean that I have data measured with some error in some noise, which I'm not specific about it at the moment. I just need some information how the noise really is behaving, and some qualitative estimates. Some quantitative estimates, sorry. Okay, so maybe a few general remarks. So I don't go into the infinite, to the finite dimensional setting. I don't discretize the problems. I will just consider them now in infinite dimensions, and I know that Mila has given a very good talk a few weeks ago, so I don't think that I have to go into the details of this. Actually, I cannot do it in the same way as she does. And I also would like to stress that I'm really considering just a pure photoacoustic problem. Whenever you talk about regularization for photoacoustics, you mainly mean that you talk about quantitative photoacoustics. I don't do it. I just want to verify the general convergence condition for the real basic photoacoustic problem, and actually not even that, even a simplified problem of photoacoustics. So whenever you see this general, I refer to the talk of Simon. So I don't do quantitative imaging, really just theoretical analysis of regularization problems for standard photoacoustics and not for quantitative photoacoustics. So let me give you this introduction what photoacoustics really is and how I view it. So probably some of you have seen this slide already. Photoacoustic imaging, Li Hong Wang calls it the method of lightning and thunder, and I really find this intriguing, so I just repeat what he is saying. Photoacoustics is illuminating an object by usually very small objects, we consider millimeter objects, with a short electromagnetic wave. It could be visible light or infrared light. It could be microwaves, and then it's called usually thermoacoustics in physics. Mathematicians don't have to differ between these two cases. And then the material actually absorbs a lot of this energy, most of the energy, and it reacts, and when it absorbs this energy, because it comes instantaneously, it expands, and by this expansion it produces a sound wave. And all what we are actually visualizing is the ability of the medium to absorb and react with this expansion. So all parameters which are in between, I don't care. I just really visualize what the overall process is doing. So the two-step conversion from electromagnetic energy into the propagation of sound waves. And when I visualize this, this is photoacoustic imaging. So here, this is an example, a very old one actually. So you typically, the object is embedded into a water tank. Doesn't have to be as big as this here one. Here is the object inside. The laser shines on it, and there's a filter. Otherwise, I don't think you see the green light as you see it here. But well, anyway, it's reality, because if you go into a laser lab, you have to get glasses. So probably this is what you see with glasses. And then there is some detectors which record the sound waves which propagate away from the medium. And from this, you then reconstruct the material inside. So the basic mathematical problem is actually very simple. So you're only interested in the propagation of the sound waves after something has some energy has been introduced. So here I write it in the form of an wave equation with a source term. So this is just the propagation of the sound wave. After the initialization, the sound wave propagates outside of the medium. This is the initialization. So this is the when you do a laser pulse, the J is a delta distribution in time, so one-dimensional delta distribution. And this is how the medium reacts. So this is what people call the absorbed electromagnetic energy. C is the sound speed, which is normalized to 1, but in physics usually considered as homogeneous. And J is the delta distribution. So this is the lightning, a short pulse. So you write down a delta distribution. But to Amel's principle, you could also write this equation usually as a homogeneous wave equation with zero source term, where you put in the source in the initial condition, and the causality gives you that the time derivative is 0. So either you consider this equation with the right-hand side in all over R, so from minus time to plus time, or you consider it with starting from time 0 with this initial condition. Okay. The infinite and the inverse problem is then we measure some pressure outside of the medium, and we construct this function. We reconstruct this function A. So now there's a quite this problem has been very well studied in many different perspectives, and one of them is that there is a relation to the circular Radon transform. The circular Radon transform is a function where you integrate over R2, where you integrate over circles. So you change here the radius, and you integrate with respect to, and here the second argument is the center of the circle. So here you reconstruct all averages. If you get rid of this t, you get you could have all averages over circles with arbitrary centers and arbitrary time. And the relation is, by PDE theory, more or less that the pressure can be calculated by integrating this. So the pressure is related to the differentiation of this factor which contains the circular Radon transform of the absorption energy. And you can write it in different form. This operator which is here is the Abel transform aside from the factor 2. So you apply the Abel transform to this energy. I put in here an H because this is scaled by a factor R3, but essentially it's the circular Radon transform. And then you divide by 1 over T and you differentiate this data. So there's a unique relation. The Abel transform is invertible. So there's a unique relation between the pressure and the absorbed energy. And so the problems, aside from the topology where you consider that the problems is equivalent to calculate the function A from pressure or to calculate from the spherical mean operator the absorbed energy. So photoacoustics is equivalent to inverting the circular Radon transform. Just to mention here, just to summarize what the inverse problem is actually doing. We measure P on a manifold which shoots around the object of interest. You measure over all the time. In practice this is not a big issue because the propagation is short enough that you can really collect a lot of this time information, and then you reconstruct the H. The equivalent problem is you calculate, you measure the circular Radon transform. This should be actually an H here and not an F. On a manifold, again surrounding the object, and then you try to reconstruct the H. So this will now our example. We will check conditions which guarantee us some convergence of regularized solutions for this particular example later on. So now, instead of solving the constraint optimization problem, I will now consider solution of the so-called Tikhonov regularized solution or convex regularization functional. So the two examples which I am considering is K is either the denoising problem, so K is either the identity, or the other problem is that K is the spherical mean operator. I forget about general photoacoustics, but consider just the spherical mean operator problem as a synonym for photoacoustics. And then we use different kinds of regularization. In my talk currently, just take the gradient U squared, or the normal, or the integral over the gradient U squared, total variation regularization, or in some cases I could also use some LP regularization. In this case, small LP regularization, in this case I just make an expansion of the function U with an orthonormal basis, and then I take some exponent, typically 1. Is the most interesting case, but all others work as well. So these are our three kind of problems which we will be considering. This is the classical one where you have a really Hilbert space structure, and this is where you have introduced on the Hilbert space a Banach space structure. So the results which you can prove now more or less, and this is what I'm interested in. So these are the only types of convergence results which I'm interested in. I assume that K is a bounded operator between Hilbert spaces H1 and H2, and the choice of the spherical Radon transform is exactly that this is the Hilbert spaces which I mentioned before, L2 and L2 are exactly that the operator is bounded with respect to the spaces. So the domain, I assume that the domain is not empty tacitly, so I assume that there is a domain. And then you have to impose something on the functional J. And here the essential thing is that you have to introduce some continuity result, to be more precise, with respect to the weak topology, continuity with respect to the weak topology. So it's a weak lower semi-continuity of the J, what we assume. And every of these functionals, so total variation, LP regularization, and in particular the norm squared has the lower semi-continuity. And then you get these results, these standard results, that if the data with noise is approximating the data without noise, you get that the solutions of the regularized solutions, which are the Tikhonov functionals, with respect to the data G delta, is converging to the solution, Tikhonov regularized solution, without any data perturbation. Okay, and also you know that the functionals itself are converging. So the convex functional, if you apply it to your solution, converge to the solution without data error. Okay, so this is more or less gives you stability, and the same for convergence. If you choose the regularization parameter appropriately, such that delta squared over alpha converges to 0, then you get the same convergence result. And this is actually the same as we have for a quadratic regularization, where you have that this one is converging strongly. And actually, because if you have here a norm, which is the standard result in Hilbert spaces, then weak convergence and convergence of the norm give you strong convergence. Well, the interesting thing for later on is a result which gives you somehow quantitative estimates on how fast the solution is converging. And there you need a condition which is quite tough. You need to get a solution. You need to see that the solution which you have can be represented, actually if you take the solution and you take the subgradient at this solution point, it has to be representable by something which is in the range of the adjoint of the operator k. So there's a relation which relates the subdifferential and the operator, and this has to be satisfied at the solution point. So we'll come to this point, to this a little bit later. Actually, but when do I have to stop?
You have 50 minutes.
50?
Yes.
Okay.
You're in good shape.
I think so. You don't know. Okay, and when you choose now this regularization parameter independence of the noise appropriately, then you see that there is a quantitative estimate of the regularized solution to the original solution, to the solution which you want to reconstruct, which is of this size, of order delta, and also the images are converging. So this is not surprising because you want to meet somehow the noise level. But this thing here is rather strange. It's the Bregman distance, so it's somehow the difference of the convex functional to the linearization. And this is written down here. So this is the one where we get the norm. And here you see that the condition on the solution enters. So the solution is evaluated by one point at the subgradient, which you have to know, and then this is somehow the distance, an appropriate distance for convex functional. So you have this result. It's not very easy to verify, especially for total variation. This is not a quite intuitive measure, but it's so far more or less the only way to get the quantitative estimates between U alpha delta and U dagger. Okay, so now let's give a few examples. What do these results actually mean? If you take J, the sparsity regularization, so you make an expansion with respect to an orthonormal system, and you take the L1 norm of the Fourier coefficient. So immediate application of the results give you that if the data is converging, the regularized solutions are converging in a weak sense, which is now the L2 sense, and here you get convergence of the semi-norms, or not convergence, and convergence of the norms. So this is converging in the L2 norm as functions, and the norms of the regularized, of the convex functional is also converging. You get also convergent, this is the stability result, and the same holds for the convergence if you really want to approximate the solution. But note you have to choose the regularization parameter in an appropriate way. And in this case, what you get out is then a solution of the compressed sensing problem, where you minimize the L1 norm of the Fourier coefficients subject to that the solution of subject that K of U is a solution of G without any noise. Interestingly enough, here you get very fast convergence, and you apply the results. You assume that this convergence this condition is satisfied. And if you just look intuitively what this condition means, what's the subgradient of a sum of L1 coefficients, it's more or less the signum function, so the sine function. And essentially, if you should be in the range and you have a function which consists of only of Fourier coefficients which are only plus or minus, it can only be in the Hilbert space if it's finite. So this means actually that the solution of this equation has only finitely many non-zero Fourier coefficients, and this is what people call sparsity. And in this case you get convergence of the Bregman distance, but it's much more in this case because eventually the solution is finite dimensional, and any norm which you get gives you convergence of the finite dimensional norm, so you get convergence of O delta. So in this case, this solution makes it actually much faster. You can generalize these results also to some non-convex sparsity regularization. Everything is infinite dimensional, so I don't go to the finite dimensional case here. So all these series is really a series and not a sum. And you can get some different convergence result. For instance, by Grasmeyer, who got order delta result, and Zaza, who got much earlier, a little bit earlier, a convergence rate of root U delta. Okay, quadratic Tikhonov regularization. I'm going back now to the very basic principle. And this is something which typically, in terms of convergence rates condition, people have not considered. And there is an interesting thing that if you look quadratic Tikhonov regularization, here the functional is J of U, is just the norm. I mean, if you want to make it even more simpler, just get rid of the U0. This is just, you take some a priori guess. And if you take in here this norm, you see that the subdifferential is actually just a linear functional of U theta minus U. And the Bregman distance is just the difference of the norm squared. In this case, the source condition means just that K star n, that the solution actually can be represented with some element of K star. But there are two interesting things. First of all, these are the results which I mentioned before. If you have norms, you get Bregman distance is the norm squared. See here? So you get the root. But you have also more convergence rates, which are for P alpha delta. And P alpha delta is more or less just defined the inverse of K applied to the solution. And these functionals here stay bounded under these conditions. And what it turns out is that these functionals are the dual variables in convex optimization. So in inverse problems, we never considered them because they have no effect on what we want to analyze. But in terms of convex analysis, these are the dual variables. And they stay bounded. Actually, they converge also to zero, but there's no rate for this. For our purpose, it's sufficient to have here a constant. Now let me just briefly sketch about when the dual variables appear. For instance, they appear when you do iterative Tikhonov regularization. This is more or less iterative Tikhonov regularization, where you put in here the difference of J and the linearization. And this method here is called augmented Lagrangian method. It's this very well analyzed, for instance, if you look at the book of Glowinski. And you have here the dual variables which are updated. So you make a process updating the solution which you want to really reconstruct, and also the dual variables. And there has been an equivalent formulation which is called the iterative Bregman distance, which is a one-step formulation of the augmented Lagrangian method. With this, well, you still need to update this one, but what you see is that if you add here j at the previous iterate at n minus 1, which is a constant term, this gets exactly the Bregman distance. So you have augmented Lagrangian and iterative Bregman, and if j is a quadratic functional, then this is equivalent to what is called Tikhonov-Morozov method. So essentially, if you take here a j a quadratic functional, all of them are equivalent, and if you look at general convex functionals, these two are equivalent and this one is different, and these two have the same convergence analysis. And the interesting thing is, now there comes the dual variable into the game. Essentially, you can prove now that, first of all, these augmented Lagrangian and Bregman distance regularization are equivalent, but you get also rates. And now rates are in terms of how many iterates you're doing, so this is this n. It's depending on the noise level, and in terms of the regularization parameters, which are these Tn, which this tau n. If you see, these play the role, also the reciprocal of this one plays the role of a regularization parameter. And here you see that you need now the source condition. This is actually also in the book of Glowinski. You need the source condition, and if you need the source condition, it guarantees that you get the same results as you have for general convex regularization functionals, and the dual variables stay bounded. So these are the ones which you come from this additional iteration, which is just an auxiliary tool, but essentially you need it for the convergence of this method. Same results here if you choose Tn more or less reciprocal of order delta, 1 over order delta. You have here the order delta result. Same here, you get root of order delta, and this stays bounded if you choose Tn reciprocal to 1 over delta. So the dual variables play an essential role in there. They have not been considered by inverse problems people for some time, but they also appear in completely different fields when in convex analysis of the augmented Lagrangian, if this source condition is satisfied. Same for evolution equation. If you don't do classical Tikhonov regularization, but assume you get the flow, which is regularizing as well, you get the so-called dual flows, and here the regularized solutions are the one when you truncate at a certain time, the solution which you calculate from this example of a certain time, then you get regularizing effects. Again, it's notable that this system, although it looks complicated, has a solution. It has regularizing properties. And if J is quadratic, it's so-called Showalter's method, which exists for 40 or 50 years already now. Okay. So now I go to the TV regularization in R2. TV, and I particularly emphasize I can only do it in R2, what I'm presenting now. So the method which is written down here is I have an operator, K, which goes from two Hilbert spaces from L2 omega into L2 sigma. So it's like a Radon transform which maps the attenuation, which we consider an L2 function, onto measurements outside for all angles of the Radon transform, angles and for all lines of the Radon transform. So sigma would be then functions, and sigma would be the sinograms, K would be the Radon transform, and U would be the attenuation. For photoacoustics, it's the absorption energy, and here it's not the diagram, but it's a sinogram for all circles. And again, Well, if there's a source condition, it looks like this. So you have to have a solution which is in, you assume there's a solution of this equation, U dagger. You calculate the subgradient, take one element of the subgradient, and you choose this one which has to be representable by the operator k star. So it has to be in the range of k star. Okay. Now our particular example was the spherical Radon transform, or the circular Radon transform, because we are now at R2. So what we do here is we formulate now the operator onto a subspace of L2 on a circular domain. You always have to assume, not always, actually it's an interesting problem with what happens when you go to the limit, but we assume that it's compact inside the unit circle, and we measure around the unit circle. But it has to have compact support with a certain distance from the origin. This is also typical assumptions which you take for the Radon transform. If this is not the case, then you get severe singularities. But I don't know how they look like for photoacoustics actually. So now the circular Radon transform maps now all these functions which compact support in the unit circle with radius 1 minus epsilon, so it's not the unit circle, but it maps it onto the photoacoustic sinogram. And you have very nice properties. It's well defined. You know how the norm of this operator looks like. It's 2 pi, and you have these nice properties. It's bounded. There's even more which helps you really to reconstruct, to analyze these conditions. And these are not trivial problems. So first of all, you know that there is a relation between, so the circular Radon transform is continuously invertible if you choose the right topologies. So here you choose, in the photoacoustic sinogram, you choose the L2 norm, and it's equivalent to the norm, to a Sobolev norm. So this is the here, which is concerns 1/2 times differentiation. So I is the operator which maps from the Sobolev space into L2. I star goes from L2 to W1/2, so it's more or less integrating 1/2, and then you take the norm of this function. So it's the usual thing which when you have embeddings that you have to have the joint norm. And the interesting thing is now it gets really interpretable what this condition means, because this condition that it's something in the range is exactly that's in the Sobolev space of this of the units, not the unit sphere, but of the sphere with functions with support with radius 1 and 1/2. So this tells you that when you apply the adjoint of the Radon transform, it integrates 1/2. This is essentially what it's saying. So the circular Radon transform maps L2 functions into the functions with space which are 1/2 times differentiable. Okay. So now, well-postness. Well, I mean, these are standard results. You know that the minimization of the functional is well-post, stable in the sense, as I mentioned before. You get convergence in the L2 norm, and you get convergence of the total variation minimization functional. The source condition now means you have to have a subgradient element which is a little bit smoother than L2. And if you have this source condition, then you get that the TV functional or the Bregman distance is converging of order delta. So here you can really characterize what it means. Essentially, this is in principle calculatable, and this is of the order. And there are many examples actually where you can check now that the source condition is satisfied. More or less characteristic function, indicator function with a smooth boundary, so it should not have corners. But this one can be characterized to satisfy the source condition. And if you make it a little bit smoother, then just by convolving it, for instance, with a characteristic function, with a modifier, a characteristic function with a modifier, then it also satisfies the source condition. But essentially for our application, for of course TV, the most important one is if you have a characteristic function, because these are the usual test examples where you want to check what TV means. So, well, there's a little bit, sorry this did not work out, but we have a report which is quite recently. But there's an interesting thing in total variation when you do it, you have to take into account boundary conditions. There are many ways how you consider TV. I usually consider TV extended on R2, and then I restrict the function of interest to a certain domain. This is the one here. And this more or less means that we satisfy some Dirichlet boundary condition. If you consider TV just restricted on the domain omega, which more or less, if you have a function which is on omega and you consider it on R2, you calculate half of the jump when you leave the domain omega. So this is why these are Dirichlet data. If you consider TV restricted on the bounded set, it's more or less like considering Neumann data. And these are the two different problems which we have to consider. And what this paper now did by Chambol, Duval, Perret, and Pon is that they could prove actually that the level sets are converging. So in contrast to what we have, that we have proven that the Bregman distance is converging, they proved for the first time a different kind of regularization. They used the same regularization, of course, but they proved now that the level sets are converging. So it's a geometrical convergence which we get. They only proved it actually for the case of the identity, but you can generalize this as we did in this report for general compact operator. So these results actually means that the Hausdorff distance is converging between the level sets of the solutions with regularization parameter alpha n and noise level delta. And here you get that the level sets of really geometrically the level sets are converging. There's a slight technicality inside. There's the regularization parameter delta n over alpha. And if you remember what Bregman distance was proving, here we could use an arbitrary constant. But in this case, you need a certain constant which comes from geometrical considerations. This is essentially coming from the isoperimetric inequality. But there's a real fundamental difference now in what has been done before, and what they did in their paper is that we get now a convergence rate for geometrical objects. So here you just for illustration processes, I just told you it can be generalized. Everything what Chambol and others did can be generalized for arbitrary deblurring operators. In particular, it applies to the inversion of the spherical mean operator. And here is a typical deblurring result. So if you look at the colors here, these are the level sets which are converging. And you see that they are geometrically converging to this comp here. It should not have really spikes because this is not covered by our theory. You have to remember that the source condition means that we have to have characteristic functions more or less which are smooth. But aside from this, you see now the convergence of the level sets. This is a different example which is for denoising. And there is an interesting thing if the object, we want to denoise this, there's a noisy image behind, but this is the ground truth, the C. This one shows you different boundary conditions if you use Dirichlet boundary conditions on a convex domain. And here we use Dirichlet boundary condition on a non-convex domain. And this one becomes actually an obstacle problem. Interestingly, for convex domains, it doesn't matter which, if the object is supported in this domain, it doesn't matter which boundary conditions you're using. But here you get, for instance, here you get these inclusions which come just from the, actually here, this one comes just from the obstacle that the domain of interest where the C is included is just this domain. Okay. So maybe I just the last thing. I will not come to the last slides, but anyway, this is the interesting thing for me, that there is now a convergence result which makes TV regularization also prove some geometrical properties. There are some differences which I hope that are technical. For instance, that there is a restriction on the regularization parameters which is not there for the Bregman theory. It's the first time that we have really convergence for an convergence of level sets for a particular inverse problem, like the inversion of the circular mean operator. And the reason why this works is that there is a convergence result for the dual variables, because actually the dual variables of TV are related to the curvature, and if you have information on the curvature, you can somehow infer convergence to the level sets. And in this way, what Chambol did is to localize all these results from the dual variable. So instead of having a local convergence result where you have boundedness of an L2 function, you can localize them. And that's a great technical achievement, I would say. I said this already. Okay, so I think I'm over with my time.
No, you have until 5:02.
5? Oh, okay.
Yeah.
Okay. Then, anyway, I just give you one. So this is now a problem which I was considering recently, and it's more or less fits the same strategy as before. So I will try to solve a regularized problem. I solve an equation, which in this case I put in here an L, is a nonlinear problem. So for instance, image registration, you have two images, I1 and I2, and you want to find a deformation which deforms the image I2 into the image I1, or opposite. And there are many things, for instance, which a registration problem should not have. For instance, you should assume that there is no, that the deformation doesn't make twists. So the thing how you can, functionals which enforce that there are no twists can be defined via notions of convexity and the calculus of variations. So they come actually from elasticity theory. You can find them in the book of Morey, and this was quite an attractive field of research, and it still is. So the thing is that we have now, we want to introduce functionals which get rid of twists. And so the first thing is U is not a single valued function in this case, it's a deformation. So it goes to a high dimensional space. So typically this U is then a vector, so it's a vector valued function, and the phi is somehow considered a gradient, so it's a matrix typically. And so there are notions of convexity. The strongest one which we have is that there is a function which is convex. So it means convex with respect to the variables u and v. X you can ignore because you do it for every point x. But this is the notion, the function f is convex with respect to u and v. This would be convex. Polyconvex, well, yeah, this is a more, I will explain it on the next slide. It's already a notion of non-convexity, but it consists of a convexity and something like determinants. So if you have decompositions of convex functionals and determinants, it's polyconvex. And then you have quasi-convex, which is a very awkward definition. And then you have other more simple to verify conditions like rank 1 convexity, but these are not really usable for us. The reason is that up to this level here, these three terms, if you decompose the function, a functional with this function f, you get the weakly lower semi-continuous functional, and this is what we need in regularization theory. So convex, polyconvex, and quasi-convex for f would be sufficient to get a lower semi-continuous functional. on a Sobolev. And if you are in n or equal to 1, even rank 1 convexity and convexity is the same. So it looks more difficult than it actually is. This comes all from this fundamental work of Ball, that if you take a functional which is convex, f is convex, and then it depends on all the subdeterminants of the deformation, which are here. So these are all the subdeterminants. Then it's a polyconvex functional. So it has the essential convexity in, because this is this function f, but it consists of the non-convex part, which are very well described or very well restricted, and these are just subdeterminants of the gradient matrix. And so the next thing is that you try to simulate convex analysis, and you have to find something like a generalized Bregman distance. And the Bregman distance is now not the linear functional anymore, it's completely non-linear. So you take the functional psi, which was our j before, it's not convex anymore, and you take here two different non-convex functionals which you subtract. So this is our subgradient. It's the functional, it's all functions from a family, or all functionals from a subfamily where you satisfy this constraint. And if you just consider this w as the linear functionals, you get the Bregman distance. So you generalize the Bregman distance to something really non-linear. This has been done in the book of Singer in 1997, and then it has been generalized by Markus Grassmeier. So I don't go into detail because this gets very technical. You have a generalized Bregman distance. You have generalized subgradients which apply to nonlinear problems. And here this is the theory. You get some generalized subgradients, which is actually not that complicated. I mean, the theory is more complicated than what you really do is. You get here all the non-convexity, like for instance the determinants you put in here. Here this is just the convex functionals where you split up the decomposition of the functionals. So you have f is a function, a convex functionals times the applied to the determinants. You leave out the determinants and then you take the subgradient. So everything makes sense. And this is more or less the generalized subgradient, which in this particular case is the polysubgradient because it just contains determinant. So it's a little bit technical, but essentially you can take all the subgradients to the right-hand side and then you can ignore them. And here this is, for instance, a regularization functional. If you regularize with the determinant squared, then you get this non-convex functional. This is the subgradient. You see it's just the constant function 2 times the determinant, and these are the convergence conditions. Eventually, if you sum up all these things in this strange non-convex Bregman distance, you get convergence rates, not the optimal but almost optimal ones, and you get the same results as in the convex regularization theory. Nevertheless, it's hard to interpret this condition, but eventually you can generalize this to a relatively huge class of regularization functionals which come from elasticity theory. And now I think I really should stop. These are the final results. And thank you.
So, questions? I have a question. If you go back to page, I think it was 15,
15.
and we had these convergence estimates. Maybe the one before when you had the yes. So that's a sufficient condition for the for that kind of convergence rate.
Yeah.
Now, suppose we don't have that. You can have any kind of rate. Is that as I understand it?
Yeah.
Is it possible that you could have a way of checking so that it could essentially have an arbitrary bad rate, but there's a way of checking that you're within the distance you want?
So you can. The first answer is you can have an arbitrary bad rate.
Yes.
That's true.
Yes.
So if you don't have this condition,
Yes, you can.
and you check.
So if I compare, suppose I'm given a linear system. I'm not suggesting that this is, but suppose I have a linear system, and I don't know the condition of a number of the matrix. I could have a tiny perturbation that could be arbitrarily bad.
Yeah.
But if I have a way of checking the condition number of the matrix, suddenly I can say something. So, because that condition is hard to verify, right?
It's very helpful.
So, is there another way? If I could construct an algorithm, I'm not suggesting for all, but if there is a way that I can at least check that now I'm close.
Well, I mean, the answer to this is, I think if you do augmented Lagrangian methods, you will see it, because as soon as this condition is not verified, the dual variables blow up. Well, it's still finite dimensional, so there is this. But in principle, you see it if you apply augmented Lagrangian.
So that means that you may not need that to be able to at least do this in practice.
No, it's just. I mean, we use it more or less in the opposite. In the opposite way. I mean, we try to interpret this condition, and then we see that there are some conditions necessary to get convergence rates. So, for instance, in the level set formulations, we think that, and I think this is really true, that cusps make problems. So we try to avoid discontinuities. But other than that, I think it's not a really practical thing.
Other questions? Please.
I didn't. You had a comment. Maybe I misunderstood that you can only show convergence of the level sets in R2. Why is it? Why is it?
Well, there's a principal problem. We need to define the operator, make the operator K well post, which means that by the PV norm we have to embed them into an L2 space. So it's really a technical thing that we need the embedding from PV into L2. And this we can do only in R2, not in R3. So R1 would be as well, but...
So what happens in R3? So in practice, what happens in R3?
First of all, we haven't done numerics because it's quite complicated. At least for the we don't have the spherical mean operator. Don't have the circular mean operator. We have the spherical mean operator, which we haven't analyzed in these details, so we don't know these properties. We need all these invertibility properties, which exist, I assume, but we haven't done them. I would assume you see the same. You see the level sets are converging. But
okay, so it's a technical thing rather than a fundamental.
Well, for instance, here we assume that we always have this operator which is bounded from L2 to something. If we can get to bounded from LP, because P is smaller than 2, it could be doable, but then we leave the framework. So I think it's a technicality. You could do it, but we haven't done it so far. But I should probably not be too optimistic. But
okay, I think we should move on with the next speaker. So let's thank Otmar again. Thank you.